the very first project started in the 17th, but they were cancelled. And since the early 2000s, I think that laser welding is a standard tool.
But nevertheless, I think we need some sort of process control because it doesn't find its way on its own. The advantage here is that you can use a very high speed between the welds.
Depending on application, we talk about like 6 meters per minute, 8, 10 meters. But we also face applications with 30 to 40 meters per minute. So the ultimate goal here is to have a tool as simple as my smartphone. I just say I want to make a weld, I put in the parameters, and the software does the actual work. But take care of your eyesight.
Hello everybody, welcome to my first Weld Lounge. In this new format, I will talk to experts and we will have the chance to make a real deep dive into technical topics. So today, I'm really happy to welcome Mr. Thibaut Bautzecher from the company Blackbird. Welcome, Thibaut.
Thank you.
And our topic today will be remote laser welding with a focus for automotive and e-mobility applications. Happy to have you here. And so to warm up a little bit, maybe you can give us some insights. How did laser welding, maybe in general, come into automotive industry?
So the very first project started in the 17th, but they were cancelled. I think the first industrial application of laser welding for automotive manufacturing was in the 80s. We talk about CO2 lasers, very different equipment from today. In the 90s, it became like a standard joining tool. Still only for, let's say, expensive brands. We talk of Audi, BMW, but we saw different kinds of laser sources showing up. And since the early 2000s, I think that laser welding is a standard tool for all automotive suppliers. Today, 20 years later, laser welding, it's part of all the processes relevant for manufacturing cars.
Yeah, no, thank you. I still remember some of the first Audi projects back in the 90s, really exciting CO2 laser versus then solid state lasers. Yeah. These were the beginnings. But when I remember, we were always fighting against the traditional welding technologies like resistant spot welding, also, of course, arc welding. I'm from the arc welding field. Yeah. So what is the main differentiation of laser welding, maybe versus resistant spot welding?
So laser welding, it's a very, fine tool to put very nicely defined seams on a workpiece. We have a very low heat input, and you can have like seams of any kind of geometry. So this allows you to have very long but very thin seams, so the flange size is limited. And the laser tool just comes from one side. If we talk of resistant spot welding, we need to access the workpiece from both sides, which limits the application of resistant spot welding. We need to have the bigger flanges, and it's a bit slow because we are using a tool that needs to touch the workpiece. We are joining, the tool is released, we move somewhere else. When we talk of laser welding, we use the light, and light is really fast. So we can make very long welds in a very short time. So we talk not just about having simpler workpiece designs, we talk of having less heat, less distortion, and also being able to weld faster.
Oh, yeah, okay. Oh, very nice, comprehensive summary. When I think about, say, arc welding, and there were a lot of applications also in car body welding with MIG welding, for example. But also there, the problem was heat input. So heat input means distortion, so that also causes problems. So I agree. I think meantime, in all middle and upper class car bodies, we find laser welding. Yeah, I think that's for sure. With the laser, we have a, let's say, really versatile tool. We have no contact of the tool itself to the workpiece. But nevertheless, I think we need some sort of process control because, it doesn't find its way on its own. So how is that done? What's the state of the art here?
Yeah, laser welding is highly automated. So it's always done by robots, linear stages. It's normally not using humans to control the process. So we need to put some intelligence into the welding process to steer the welding at the right place. This is what we call seam tracking. So we need something like a sensor that looks, where is my edge? Where do I want to put the laser? And then we make sure to put the laser at the right place. Because we talk of a laser spot diameter of less than a millimeter, something like 500 micrometer, going down to 30 micrometers. So seam tracking is important. And then in process monitoring, what happens in a weld? How good is the weld? So we got like optical emissions, for example, that we can record with another tool, a sensor, and then we can compare the data. Was this a good weld? Was it faulty because there was like a gap, for example, some dirt on the weld? And then very important, once the weld is finished, we look at the seam geometry. How is this seam looking like? Do we got like open holes? Did we weld it all, for example? Is the seam at the right position? So process monitoring, it's an important tool. It's part of laser welding to allow this highly automated laser welding application.
Yeah. No, I think that's very important, and it's highly integrated. Yes, this process monitoring and sensor technology into the laser process itself. So that also means it's a lot of software involved to have all this controlled. But just maybe for our visitors, a lot of laser welding techniques also work with, let's say, tactile optics. But let's say working with a tactile optics, that's also a kind of sensor because it's, let's say, like a touch sensor. And especially if you have overlap welds, you use maybe a tip or the wire itself as a sensor, but this works only very restricted for some special joint geometries. If you would compare tactile laser welding with remote laser welding, what are the main differences?
Yeah, tactile, like you said, you use a wire, for example, to guide the welding process along the edge, which is nice because we have a very easy setup to find the place where to weld. In case of remote laser welding, we need this additional sensor. Tactile welding is closer, giving you maybe a disadvantage because when we do laser welding, we have like spatter, we get metallic fumes. If we do remote laser welding, we are more elongated. We can have like a distance up to 1 meter or even more than that, giving you more possibilities to get rid of the dirt coming up from the process to protect the welding equipment. So again, we also have to talk about the application. Sometimes you need additional filler wire to fill the gap. This is something you cannot do with remote laser welding. In case of remote laser welding, if there's a gap, this might become an issue unless you got a sensor that can detect this gap and it can bridge the gap, for example, by having some beam oscillation to allow to melt more of the material to bridge the gap.
So in remote laser welding, as you said, restrictions could be, let's say, if your fixtures are not precise enough, that you cannot overcome these gaps. For them, special materials where you need filler wire, otherwise you would have, let's say, weld cracking. That could also be a problem. And for some, let's say, very special alloys, also, let's say, shielding gas could be a problem. Because unless like in arc welding, here you are like 1 meter away from the weld. So it's not so easy to guide some shielding gas there.
Yeah, but again, with remote laser welding, we have different possibilities to improve the process. So the application without shielding gas, if we talk of aluminum welding, for example, for car doors, in the past, there was shielding gas involved using the filler wire with tactile optics. Today, there's remote laser welding. It took a long time to understand how with only using the laser light, I can have a nice joint without having cracks, for example. This can be done by modulating the oscillation, the laser power of the beam, having the right beam diameter. So there's a lot of know-how involved in here. How do I bring the laser light into the workpiece? Because the laser light here, it's a very sharp tool and we need to use it precisely.
Yeah, I think that's one part of, let's say, the special advantages of remote welding. Let's say the quality that you can achieve by different weld geometries, as you just explained. I think the second very important advantage is speed. And let's say you mentioned the door applications, but it's also for others like car seats, it's used widely. The advantage here is that you can use a very high speed between the welds, where normally you have the same speed of the robot, so you do a weld, and then you go to the next point where you have to weld, and that's quite slow. But with remote laser welding, with these scanner optics that are involved, you can increase the speed between the welds, and that means very, very high productivity.
Oh, definitely. I mean, jumping from having the tactile optics to remote laser welding optics that are like fixed, you need the robot to guide the beam. if you talk about the scanner you just mentioned with the mirrors, we can deflect the beam in milliseconds. So we can process a whole car door in just a few seconds. I mean, of course, we still need a robot to move the welding head. The welding envelope of a scanner is something like the size of a piece of paper, like 30 by 30 centimeters. But within this area, the laser can move at very, very high speeds. Of course, the welding speed is limited. Depending on application, we talk about like 6 meters per minute, 8, 10 meters. But we also face applications with 30 to 40 meters per minute. Yeah. And this can be done easily because we just deflect a little mirror and the light goes where we want to have it immediately.
Yeah. Oh, this is amazing. You're comparing it to arc welding, I always have to come back to this. We talk about, if you weld fast, it's 1 meter per minute.
Yeah.
And everybody was excited. And for laser, it's nothing.
Yeah.
Let's say we touched some applications like doors and car seats. Can you give us some more examples? What are typical applications in let's say, automotive or nowadays e-mobility?
Yeah, the car seat, the body, the door, these were the typical applications where the laser is still in use today. But if we look at all these new applications, like the e-mobility, there's more laser being involved. So e-mobility, of course, we talk of workpieces, of parts that have to conduct electricity, metallic parts, aluminum, copper, and we talk of high amounts of parts. You don't have one battery, you have like a few hundreds of batteries. You just have one engine. But this one engine has something like 200, 300 joints between thick copper wires. And this is done with the laser welding. Of course, there are also joining technologies other than laser welding, talking of ultrasonic welding, for example, or typical welding applications. But the laser here is used because it's fast. We talk of mass production. And someone who is building cars, he is not building cars because he wants to build cars and have nice seams. Maybe he wants to earn money. So productivity is important. And like we just said, having this mirror that can easily jump between welds, it's a nice mixture because we got very small welds on these batteries, on these copper parts, and we have a lot of welds. So the laser light needs to travel fast. So today in a car, we start by welding the battery, the cab can welding. We got the bus bars that are connecting all the battery poles. Then we got the power electronics, where from direct current we make alternate current. Then we get the stator with the hairpin connections. So we talk of a lot of applications, different materials, high numbers, and the future is nice because we talk of rising applications in future.
Yeah, which is good for let's say technology development, of course, in general. What I'm experiencing looking at these applications, let's take hairpin welding, you always need some sort of process control, process monitoring. Yeah. So, and what's always like the magic abbreviation that's used, it's OCT. So optical coherence tomography. So just for everybody, can you say some words about that special technology?
Yeah. So let's go back 20 years in the past. Normal standard welding optics, fixed optics, they used cameras for seam tracking, for seam inspection, for looking at the shape of the melt pool, for example. And camera technology is widely available. Everybody knows how to use it. If we talk of a scanner, the scanner is traveling very fast in different directions. And if you want to make seam tracking, you have something like laser triangulation. So it's not just the welding head, you also have external sensors looking at the welding process. But in case of remote laser welding, these tools would have also to move very fast. This is not possible. So we need a technology that works coaxially, that goes with the laser beam through the processing optics. And cameras are maybe limited in some of these applications. For example, if you want to track a joint, we talk of making an elevation profile. It's not possible by just using the camera. OCT is something not new, but new for laser welding applications. Introduced something like 10 years ago. It allows you to give you a 3D picture of the welding process. So in front of the welding process, you get a height profile of the geometry of the workpiece. You can get a 3D picture of the keyhole. So you see how deep was my laser beam going into the material, which is a really nice information because you don't have to make cross-sections afterwards. And it gives you in real time a 3D picture of the welded seam, all in one tool. So we've got one welding tool attached with an OCT, And immediately after the weld, you get information about penetration, about seam geometry. And this is a big potential for OCT, still in the beginnings.
Yeah, no, it's really versatile, this tool. So we call it, let's say, like pre-process, in-process, post-process monitoring. So in all three stages with one tool, it's fascinating. You would, let's say, before that you had three different sensors, and and they were not as fast as OCT. So that's a real progress here. But it also makes it very complex. But nevertheless, it's very widely used. It becomes more and more attention.
But if you say complex, if I may interrupt, it's only complex if the accessibility is hard. Of course, if we talk of sensors and we talk of different components, it looks like a system for the laboratory. But the goal of all suppliers is to make something user-friendly. I mean, we talk of mass applications around the world because cars are built and supplies are everywhere. So the ultimate goal here is to have a tool as simple as my smartphone. I just say I want to make a weld, I put in the parameters, and the software does the actual work. And of course, this is work in progress. We don't have these solutions today, but there's a need. And so I don't think that this will stay complex. We are thinking of having intelligent solutions, and the sensor, it's part of the whole system. And you don't program the sensor. You just say, I want to weld a car door, and you press play. Ask me again in like 5 years. Maybe we are like a step closer to this solution.
No, I absolutely agree. This is, let's say, in the beginning of, let's say, a broader application range. Remote laser welding on itself, it's very widely used, and it will grow, especially with e-mobility and also in other applications. I think still the other, let's say, laser technologies will still remain, because sometimes you have the need for, for example, tactile.
Yeah, of course.
Or then you have other parts where you would have still a conventional optic. If you look like gears for cars, you don't need a very sophisticated optic. You just do it, and it's also a laser application. So I think every specific application will still have its field. I hope for arc welding there will still be some applications remaining. But I think, let's say, like for sticker plates, for other parts, there will be enough room also for the arc welding processes. So when we talked about, let's say, this, say, high automated and very sophisticated processes, what we also see since maybe 1 or 2 years coming more and more is this manual laser systems. I'm sure, of course, you also are observing this trend.
Well, this is something, let's say, interesting, because traditionally in the world of laser welding, we talk of highly automated systems, a lot of sensors, a lot of engineering experts taking years and years to set up the system, the laser welding cell. These handheld laser welding solutions, they're very simple, but maybe there's a market. There will be a market for these applications because there are people that want to weld in their garage something together. And if it's the laser welding process because it gives a nice quality and the price for a system is good, well, then it's a market. It's just very different from the automotive application that is like highly sophisticated. But there's one issue. Laser light is dangerous. You will never get rid of the danger from laser light because you can't see it. Laser light is not 1 milliwatt like the laser pointer I got at home. We talk of a few 100 watt, maybe even kilowatt one day in those handheld devices. And laser light, that's not for kids. This is very dangerous. So there might be a reason to use these solutions, but take care of your eyesight.
Yeah, no, I absolutely agree. I see it also more as, let's say, maybe a competition to traditional TIG welding, but the safety issue has to be resolved. And of course, we hope this will be done. It's a new laser application. We are, of course, in favor of all new developments as technical experts, but always safety first.
Exactly.
Yeah. So let's sum up a little bit. I think we covered the field of remote laser welding, of course, with a focus in automotive and e-mobility, where it's mainly applied. So thanks a lot for the insights. I learned a lot, even as a weld prof. And so thanks a lot for your input, Thibaut.
Thank you for having me here today, Emil. Thank you.